This is an introduction to section 17.1. Remember when we started off this course, we looked at kinematics of a particle, and then in chapter 13, we used Newton's second law and looked at kinetics of a particle. In chapter 16, we did kinematics for a rigid body. And in addition to using position, velocity, and acceleration, we had angular position, angular velocity, and angular acceleration. And we saw that the equations that we had for kinematics with the angular position, angular velocity, and angular acceleration were pretty much the same as what we had in chapter 12 for position, velocity, and acceleration. Now, in chapter 17, we're going to be looking at kinetics for a rigid body. Back in chapter 13, we were using Newton's second law. In addition to Newton's second law, in chapter 17, we're also going to be using an equation which looks similar to Newton's second law. In Newton's second law, we had the sum of the forces. In our new equation here, we have the sum of the moments. In Newton's second law, we had acceleration. In our new equation here, we have angular acceleration. In Newton's second law, we had mass, and in our new equation here, we have moment of inertia. This equation you have actually seen before in Physics 161. In section 17.1, all we are going to be concerned with is calculating the moment of inertia. So we used this equation before in Physics 161, except that instead of calling this the moment, we called it the torque. So the net torque is equal to, or the net moment is equal to the moment of inertia times the angular acceleration. But in Physics 161, we didn't often calculate the moment of inertia. We often looked up the moment of inertia in a table. And in fact, on the back cover of your dynamics textbook, they give you the moment of inertia for different shapes, but we're going to learn how to calculate the moment of inertia for these different shapes. And they give you the equation for calculating the moment of inertia on page 410. This is equation 17.1. In this equation, r is the perpendicular distance from the axis of rotation to a small element of mass, dm, so that's shown in the figure over here. And if you look at the thin ring, which they have on the back cover, for any little mass that you pick on the thin ring, this distance r from the z-axis to that element of mass is going to be the same. So in the case of the thin ring, r is not going to be changing as you integrate all the little pieces of mass. And so you could pull r squared outside the integral and then just add up all the little pieces of mass to get the total mass. That would give you r squared times m, which is in fact what we get for the moment of inertia here. Okay, but in other cases, when you do the integration here, r squared is going to change depending on what element of mass you're looking at. So let's go and look at, for instance, the thin circular disk. If I pick a little piece of mass here, then r is not the same as picking what it would be if I had a little piece of mass on the edge of the thin circular disk. So I don't really want to integrate with respect to m in that case. I'd much rather integrate with respect to maybe x, y, or z. What we're going to do now is very similar to what we had in Physics 261 when we had an integral and we were integrating something with respect to q. So our integral, let's say if we were calculating the electric field, we would have the integral of k dq over r squared in the r hat direction. But we didn't really want to integrate here with respect to q. And so instead, we did something like this. dq is equal to the volume charge density times dv. And so I could take this and put it in for dq, And then I could do the integral that way. And in physics 261, it wasn't always the volume charge density. We also had the linear charge density and the surface charge density that we could use. But for the sake of comparison here, we just want to look at the volume charge density. Okay, so in this equation here, when we have dm, this was the charge density. Oops. This is the charge density. This is the volume density. So this is the density that we usually talk about. So that's the mass of the object over the volume. So they tell you here, dm is equal to rho times dv. So then we can do something similar here. So this was for physics 261, and this was a charge density. If you're using the mass density, you have dm is equal to the density times dv. Or another way of writing this would be the density is equal to the mass divided by the volume. If you have a uniform density, then it doesn't matter what mass you look at. So if you pick a little piece of mass here and divide it by the volume that you have here, if it's a uniform density, if you pick another little piece of mass here and divide it by the volume of that mass over there, it would be the same. So for a uniform mass density, you can say the total mass divided by the volume gives you the same ratio as any little element divided by the mass of any little element divided by the volume of that element. In physics 161, we only ever looked at uniform volume charge density, so that could always come outside the integral. But actually, I don't remember in this course if we're going to look at any densities that aren't uniform, but we could. If they don't give us any problems like that, we could make some up for ourselves. Okay, so we're going to use this if we can't pull r squared outside the integral to rewrite dm, and then equation 17.1 becomes equation 17.2, and now you're integrating over the volume. This is going to turn out to be a triple integral. So you could write dv as dx, dy, dz, and then you have to do 3 different integrals. Okay, so this would be for rectangular coordinates here. On page 411, they show you 2 different ways that you can calculate the moment of inertia. You can use a shell element or you can use a disk element. So we'll talk more about those when we do some example problems. And on page 414 and 415, they make a few other points about the moment of inertia. So you can use the parallel axis theorem. So on the back cover of your book, they give you the moment of inertia for different axes that go through the mass center of the object. But suppose you want to look at an axis of rotation that does not go through the mass center of the object. Then you can use the parallel axis theorem, which says the moment of inertia going for an axis going through the mass center plus m times d squared, where d is for another axis which is parallel to the one that goes through the mass center. So z prime here is going through the mass center. This axis here, z, is parallel to z prime, which is going through the mass center, and the distance between those two is d. So if you took the moment of inertia for this axis, which is something you could look up probably if it's a common object, then you could add m times d squared to that to get the new moment of inertia rather than having to calculate this from scratch. Okay, so we have the parallel axis theorem, and also sometimes when you look up the moment of inertia, rather than just telling you like this is the moment of inertia for this object. Instead, they may give you the radius of gyration, and using the radius of gyration, you can find the moment of inertia by the radius of gyration is k. You can square k and multiply it by the mass to get the moment of inertia, which means you could also find the radius of gyration by taking the square root of the moment of inertia divided by m. And finally, on page 415, they tell you that if you have bodies that are made up of different pieces, or maybe something like a disk where you have a hollow part, so that's like a disk with an outer radius here minus the inner part here to give you the hollow disk, like the whole subtracted from a solid plate, then you can, for your calculation, add the moment of inertia for the individual pieces up together to get the total moment of inertia. Okay, so that is our introduction to section 17.1.